Okay, I'm going to be doing an entire, let me make sure, yes, audio is working, an entire walkthrough of this 2024 exam 2. Again, sorry about the audio on the last one. I'm going to do a similar thing, actually. I'm just going to do like a 10-minute overview, like how to solve each question. But hopefully this one, it's a bit longer, like the work and really the logic of why we apply that work. Again, just a preface since it got cut out on the last one. Uh, Units, if you didn't watch the last videos, I don't, since the multiple choice answers aren't off by like magnitudes, but rather values, the metric units like these and these, you just don't have to convert them. Is what I would have said in the last one, in the last chapter, or last exam. Here, when exponentials and like the signs and square roots and stuff, it can get messy. So be careful with it. Take it with a grain of salt. That being said, let's just get started. Okay, let me grab my red marker here. All right, immediately starting off with a tricky question here. So long after the switch here is closed, how much charge will the capacitor have? So you have a capacitor, right? Once it starts getting power, it will gradually grab all the voltage until there's like, or it will like store power here until there's no more like amps, no more current running through the wire. So we know there's no actual current running through this portion of the circuit long after the switch is closed. What does that mean? Well, what it means is that in terms of like division, right? We don't like really treat this as like something we have to consider, right? Because this has no amps, we effectively just look at it as like the two resistors R1 and R2. And we essentially just say, okay, these are, worth equal amounts. So you do the math, they each get 3 volts. But is that just because this section doesn't have any current, it still gets the same volts as it like as R2 does, because like technically they are set up like this, right? So even though this might not be getting any current, and so all the voltage is just getting split among this path and this path, technically speaking, the like even that way, because there's no like amps to use it down here, this still has 3 volts down here, because if this upper one has 3 volts, the lower one also has 2. That's just how the diagrams are set up. This has 0 amps, but 3 volts long after the switch is closed. What does that mean? Well, Q is just equal to CV. So if you multiply the C3, 3, you get answer just fine. All right, this is just a straight up annoying like resistor circuit problem. Let's solve it. I'm gonna need like, honestly, give me MS Paint for this. I'm probably gonna need the room. So how are we set up here? Okay, so we have, again, I like to draw these kind of like in a line. So just like look at where it starts with the EMF. What do we encounter first? Oh, R1, then it splits into R2 and R3, so on and so forth. So first we have R1, which say this is 100. So then it splits into R2 and R3. So R3, this is the 200 ohm, and this is going straight to the end. So a little bit of foreshadowing, but we're just going to drag that over. Then it splits, after R2, it splits again into R4 and R5. So R4 here is also a 200 ohm resistor. Squealies, just because I, want to not waste my time drawing squealies mostly. And then, R5. R5 is also followed by an R6. Wait, what am I doing? sorry, what am I doing? R1 splits into, oh my goodness, what have I done? What have I done? R3. And then R2 here, and then the R2, skipped a step. The R2 splits into R4 here, and then R5, R6. So then follow along again, combines with the R4, and then it later combines with the R3 and goes back into the battery. Okay, so we're told that R3 dissipates 20 milliwatts of power. That is this resistor down here. But what is milliwatts? What is that? What does that mean? Well, we know it's resistance, right? So I'm not gonna worry about the units here. If it's got 20 power, and we know that it is 200 ohms. Actually, I think I do have to worry about the units here. -3. If we know it's 200 ohms, we can square root what we get from dividing that in order to get the I here. So I is equal here to 0.01 amps. And it's also equal, if you just multiply the 2.01 times 200, you can do the power equation. 2 volts is going through here. Now, since 2 volts are coming on the bottom, we also know that 2 volts have to be coming up here on the top. That lets us solve the amperage here, which is 0.02 amps. And then we know that, there has to be 0.02 amps distributed in this section here, which is nice for later. Let's simplify the circuit a little bit more. So what we can start by doing, just copy paste this, is we can combine these two, right? In series with resistors, they add, so we end up getting a 200 here. Okay. And stupid. This is stupid. I'll draw some arrows. Whoop, whoop. And then these 200s in parallel, they will, the funny 1/ohm thing. The thing about if they're the same, you just half it. So since they were both 100, they just become, or since they were both 200, this just becomes a 100 ohm resistor. And resistor here, this will get the same amperage and obviously also the same volts. So now we're getting somewhere. So we'll 100. The 2 on the top, again, this is going to be 50 because we're having it. And we get a 200 on the bottom. Am I doing this correctly? Let me reference my material. I don't want to waste my time doing this wrong. I'm not sure I am doing this correctly. I think I messed up somewhere. Who knows? YOLO. So we get this. Yeah, I think I did mess up somewhere. Where did I? This adds to 200. I could have just put the wrong thing somewhere. I mean, I get you. Even if I'm doing this wrong, I assume you can see how to do it. Maybe there's someone screaming at the screen somewhere. Double check. 100 goes to R3 here, and R2. Then R2 splits into R4, which is correct. R5, R6, perfect. This merges into 200. Gotta make sure I got my, yes, that's correct. That's how it works. And then I'll check again. 1/200 plus 1/200. That is indeed 100. Yes, that it did work like that. Oh, okay. Yes. Of course, when you in this case you add them. You don't. Literally my last step there. Yeah, so you add that. Each of these, well, the amps will be the same. It'll still be 0.02, and the voltage you'll get multiplied is now a 4 volts. Does that make sense? I don't know. And then 100, this can get put into a 100 configuration. Add the amps, 0.03 amps, or 3 volts. See, there's something messed up here. 0.02 times 200, that's 4. And how come it's... What did I do here? Dude, how stupid am I? Sorry, guys. I got 5 hours of sleep. It's hitting now. Approximately now. What did I do here? 0.01 amps. And then I said that this one needed 0.02. Okay. And you added those, and then that stayed the same. So we get 4 volts there. That sounds about right. It sounds about right. Anyway, I think I'm just maybe being dumb. I'm definitely doing something dumb here. It's I guess. Why are there different voltages for the same thing here? Why are there different amps? Shall we diagnose that first? It should not have been split as it was. Why did I give the top one 0.02 amps? Why did I do that? You can pretend I just didn't do that. I'm sure I had a reason. Was it a good reason? Who knows? Oh, it's because... Wait, why did I give it 0.02 amps? Was that a miswrite? It was supposed to be 0.01 because it's the same as the bottom layer. Oh my god. 0.01 times 100. It's 1 volt up here. I don't know what I did. This is 1 volt. Oh, goodness. Oh my goodness. Oh my goodness. 0.01. 1 volt. 1 volt. 1 volt everywhere. This becomes 2 volts. So yeah. This is 2 volts. Oh, I'm sorry, guys. And also, it's 0.1 amp up here, which becomes 0.2 amps up here. But then this is also 0.2 amps, so it's also 2 volts. And you add them together, you get 4 volts. That's all it is. Oh my goodness. Wasting your time. Sorry. Okay, let's get back on track. But I mean me. I gotta get back on track. So this is one of the ones where you have multiple EMFs, multiple resistors, which means currents, because you have these junctions, and at each junction the current will change. So just by looking at it, right, we're kind of getting like current up here, current up here. We can, deduct that there's a current like down in here. So I'll label my currents here as an I2 going down here, and an I3 going up here. So again, it doesn't matter if you're wrong with like the arrows. It'll flip itself out eventually. Don't worry about it. So the first thing to do, look at the junctions, right? You got I2 coming out, I3 coming in. Since the sum of the junctions is 0, we know that I2 is equal to I3. What I then recommend here is look at the loops including this I2, which you can replace. So the first thing is this little loop here. And what do we got here? So we got this EMF here. So EMF 1 is 10 volts. So we're actually solving for this EMF 2. It's a bit of a, I don't know, unorthodox way to do it, but it's cool. EMF 1 is 10 volts. And we pass the resistor 1 here, and the resistor 4. All resistances are 10, so I'll just group them together. But basically, IR for each of them. I here is I1, and the I here is I2. And then we also have this unknown EMF. And you have two I3s getting hit, right? One this way and then one this way. So what we can say is we can go like 10, and we'll say 2I3 plus I2, that I2 in the middle again from R4. Then we can sub some stuff in here. So I'll say is this oh yeah, okay. I was gonna say we do need an extra piece of groundwork to solve this problem. Big hint: the current through resistor R2 is 0. What does that mean? I3 is just 0, right? So I3 is 0. That's why it pays to actually read the question sometimes, which means that this EMF is actually equal to 10I2. So with that in mind, let's sub in for I1 here. So I3 is 0, so I1 is just equal to I2. So let's sub in for I2 here. So 10 equals 10 I1 plus I2. Again, they're equal, so 2I2. Or I1s. I'll do the I2s is what we want. So that means that I2 is equal to 10 divided by 20, or 0.5. And in here, we, I mean, it's 10 times I2, which we know is 0.5. It's going to be 5. There you go. Oh, more stuff, more things. Okay. So here we have one track, 100 ohms, goes straight to B. I'll redeem myself on this one. How about that? I messed up last time. 100 here, 100 here, 100 here. These two come together. Equivalent resistance. Okay, so we can say there's 100 here and 100 here. When there's two of the same, again, when we combine them, we can just have them. So, boom. Then we can add the resistors in series, 150. And then you will need to do this on the calculator. 1 over 100 plus 1 over 150. It gives you 60. So, boom. Okay. Let's get to the fun stuff. So an electron moves with velocity in a uniform magnetic field and an electric field. So the net force is 0. What does that mean? The electric field has to cancel out the magnetic field. Let's check out the formula sheet. Look here, we can see the formulas for the electric force and the magnetic force. So simply put, the electric force has to equal the magnetic force. About the direction later, we'll solve for magnitude first, which I guess we know is one of these two, but I digress. So the charges cancel, and we're just left with if we want E, we just multiply. Guys, it's 6. So let's talk about the actual magnitudes here. So let me draw a little graph here. I, J, K. So the electric field is headed. Well, we need to figure out where the electric field is. So the electron has velocity minus j, so it's moving in this direction. This is the v vector, and the is here to positive k, so this will be the b vector. So we're just going to do right-hand rule. V on the bottom, pull towards you for that, and then remember, since an electron is negatively charged, you'll see that it's heading to the right here. Okay, well, where does so we're being forced, the electron is currently being forced to the right, so electron field needs to force, So you might think, oh, it's negative I. Remember that in an electric field, the negative particles oppose the direction of the field. So if the electric field is pointed in this direction, the electron will actually be forced to the left. So hence positive I. Here. Okay. So we're entering an electric field with a certain velocity, and you meet an orbit. This is a very generous hint. Telling you to divide x by 2. I don't know how I feel about that, but here you go. R is equal to mv over qb. Let's see what we can do with this. mv over qb. We have our R. We have m. We have q. We need, or we have v. We need b. So let's take a look. B is going to be equal to mv over qr. Everything into the calculator here. 1.3 times the V3 divided by the Q, 1.6, divided by the R, which is just 2.5 divided by 2, 1.25. I get 1.9. Now the issue concerns, is the magnetic field, like, where is it oriented? Is it going into the page or out of the page? Well, let's think about it. The particle is currently heading upward. I guess you're probably... How is this? Is it mirrored? No, it is not mirrored. So the particle is headed upward, and it ends up curving to the right, which means that there must have been a force that pushed it to the right. So we know that the force, which is like represented by the thumb in the right-hand rule, is to the right. Now, the velocity, it starts off up, right? If we, let's say, make the electric field into the paper here, so I'll say, no, I'll keep doing it like this. Into the paper, it looks like, oh, it's going to the right. But remember, electron gets flipped. It actually goes left. If we instead take it, it's going velocity upwards. I'm going to do it in mine because I'm confusing myself. So velocity is upwards. And it goes, I'm confusing myself, dude. Velocity upwards. It's positive, sorry. The charge is positive, so that's correct. Sorry, I was confusing myself. Upwards. If you go out of the board, it'll go to the right, so that's correct. If you go into the board, it just goes strictly to the left. You don't flip. But yeah, it's 1. You can do it yourself. I was trying to orient with the camera, but it's hard. So, direction of magnetic moment, direction of the torque. I feel like there's got to be a question like this on the exam, and it's 3 points. You just have to know how to do it. The magnetic moment is like normal to the area. What you can do to find the direction, curl your fingers in the direction of the current, and then wherever your thumb is sticking, that's where it is. So my fingers are curling this way, my thumb, boom, done. Now, torque. The magnetic moment wants to be parallel with this B field. So in the spring 2023 exam, there was like the magnetic moment. The B field was like here, and the idea there was it moves counterclockwise, right? If it was up here instead, it would move clockwise, just to align itself parallel to the B field. Here, it is already aligned parallel to the B field, therefore no torque. 1 is correct. All right, what is the net force, magnitude, and direction on the loop? Let's draw our little current lines here. The interesting thing here is everything's in the B field, but the B field based on x. Now, what does that mean for the y's? Well, the y's, this is all just like, or these are kind of like, you might think, oh, do I have to like integrate or whatever? No, you don't. Ultimately, right, if the current's headed this way, and the B field is into the board like this, this side's forcing upwards, this side is forcing downwards. They're all equal because like one side or one dot here will match one dot here. They'll cancel. Don't worry about it. What you care about is the left and right side. There's usually always stuff that cancels whenever you see a square. You only worry about 1 or 2 sides at once, usually. So on this side, we have a force. So current's going upwards into the board. We're headed to the right. So this is headed to the right, forcing to the right. Meanwhile, here, down, this one's being forced out to the left. when we actually solve for this, so on this left side here, so left, I'll say force to the left, it's just going to do ILB here, this one here. Everything's perpendicular, so we don't have to worry about angles, cross product, we just multiply. So what is B? B is actually 3 times 2 times x. So we're going to multiply I is the 4 times L, 2, and then B is actually just going to be 3 plus 4, right? No, it's not. It's going to be 3 plus 2x, x is 1. It's going to be 5. 3 plus 2. So 4 times 2 times 5, you get 40 here. Now, let's look at the force to the right. Again, it's going to be ILB, but here B is changed because of this. So you still multiply 4 times 2. Now, what is B? B is 3 plus 2 times 3, 6. So 2 times 9 total, you get 72. Again, these are opposing charges, or opposing forces. So you take their difference, you get 32 towards the right, which is the positive I direction. Okay, this is a classic question. So the idea here is you have a point surrounded by circle wires. These don't matter, but one's heading, since it's continuous, one's headed got the current in one direction, one's got. So real quick, if you have the outer loop, right, it's headed to the right, the current's headed to the right. So when it reaches the point in the middle, it'll be going into the page. So just make a note of that. This one goes into the page. Here, this one, the current's going to the left, so it's coming out of the page. So quickly make a note there. Now, we just have to use this formula here to get the center of a circle. We're not at the center of a full circle, but rather at like a half circle. So we just divide by 2. So u naught I over 4r is what we want here. Now, what does that actually mean for us? Well, the only thing that is different, right? U naught I and 4. We only care about this 1 over r term. That's what changes between these two. So we'll start with the inner circle, right? 1 over r. It's radius 1 centimeter, so 1 over 1 is just 1. And then again, they're opposing, so we subtract. This is the inner. This is the thing that's going out of the page. And then this is R2, so 1 over 2. This is the force that's going into the page. Again, we subtract because they're opposites. They're canceling each other. So at this point, u naught is equal to 4 pi, so the 4's, we can cancel them. Pi, multiply the amps by the amps of 2, it's going to be a 1/2 term. So we divide by 2 again, and you end up just getting pi, because I didn't do this. And so, yeah, pi magnitude, pi, and again, since this term was the one that was into the page, and this kind of, or out of the page, and this term was greater than 0, we know that overall it's coming out of the page. And again, anything that's closer to P will dominate it, right? Into the page has less effect because it's further away from P. All right. For wires carry I into or out of the page as indicated in the square. Where's the direction of the magnetic field? At the center. Start at the top left here. So that is, well, it's coming out of the page. And when you curl, you can see that it is in a counterclockwise direction. What this effectively means is you get a sort of like arrow like this. Right? Again, out of the page, counterclockwise, you'll get something like this. These two at the bottom, they're coming into the page. They are clockwise, right? Clockwise here, which means that you'll get like this on C. And here, again, it's going to be clockwise, which means you'll get an arrow like this on C. And you can see there's all one thing in common, right? These are both canceling each other's y components out. These are as well. but they're all going to the right. So overall, you're just going to be heading in the positive I direction. All right, wires. We want to essentially figure out what force each wire has on wire 2. So in order to do that, we'll use this equation probably. Because wire 2, yeah, it does have an ampage. So mu naught over 2 pi. I said this in the last video, since mu naught is like 4 pi times 10 to the whatever, I just like to write this as 2. So 2 times L length, so we ignore L, so 2 times IA IB over D. Right, so the equation we're concerned with is 2 IA IB over D. Figuring stuff out, we'll say I2 is always going to be on the outside here, and we basically want to calculate all the IBs over Ds. Now, we'll say, so, well, I'll start plugging stuff in. This I2, it's equal to 2 amps. So we'll say into the board is positive. So we can like put a 2 in here, right? When we look at this 1 here, we notice that it's going out of the board. So we'll say it's negative 1 amps. Additionally, we'll also say that since it's headed left, we'll give it a distance of negative 1. I'll come back to that as well, a little more rationale there. But again, this 3 into the board, we call it negative 3 over the distance 1 plus, and then here into the board, it's positive 4, distance 2, positive 2. So what do we have? We have 1 plus 2 minus 3. This just ends up being 0, no net force. And again, coming back, I made the directions negative. This is kind of like that thing where, like, we'll say into the board is left, or out of the board is left, and like into the board is right. This is kind of like this homework problem, where basically you see that like these two are going opposite, so they like, so this is like pushing a force like this here, and like this is pushing a force here. So even though they're both same distance away and same like relation in terms of how the current is running, they're going to have opposite effects on the force. And so like this one as well, it will have a less significant attraction force, like so. But okay, yeah, it also scales by like I, so we can't based on this alone. But you can see that it depends on what side they're on, how they're pushing. Okay, this question asking us for the integral BDS. If this looks familiar, it's Ampere's law. So we're actually just solving for this mu naught I enclosed. Mu naught I enclosed. Beautiful. Now this wire carries a uniform 2 amps. Take a wild guess on how much is in the path. That's right. It's half of that. It's 1 amp. So this contains 1 amp. That's the charge enclosed. Again, it's worth checking, right? This wire, or rather, we'll check with the this thing here, right? This would headed in the clockwise direction. It would make a current, or like a magnetic field going this way into the board, whereas this one's headed out of the board. So whatever we find, we will have to put a negative sign in, because it's just opposing whatever, like, yeah, the field from the outside and the path there, they oppose each other, so we have to negate it. And so then at that point, we just do mu naught times 1 and stick a negative sign in front. So like 4 times pi, you get 12.5666. You know, it's going to be negative sign. You get A. So the current I in the long straight wire is increasing. What's the direction of the induced current in metal loop A and B? First of all, long straight wire increasing. Let's take forces that make. So we're going to have right-hand rule, something like this happening, right? That's where you're going to be curling your fingers. That means that at this point, when you hit B, you're going to be hitting B, anything here into the board, right? Inside or outside of B. Additionally, we're going to, coming up here, we are coming out, right? Coming out of the board here and here. So that means that going into the board here and going out of the board here. And this is increasing. So the idea with the flux, the little wires will try and work against the little changes over time. So here, it was coming out of the board, and it's going to come out of the board even more. Into the board. Wait, or was it the other? My drawings. Maybe I should be using dots and stuff. It was coming out of the board. It's coming out of the board a little bit more now since it's increasing. Here was going into the board. It's going into the board a little bit more now because it's increasing. And B wants to go out of the board a little bit. A wants to come into the board a little bit to cancel this part out. So if B wants to go into the board or out of the board, then it has to induce a counterclockwise current. And if A wants to go into the board, it wants to induce a clockwise current. So hence this one. Okay, coils. So we have a coil. Oh, yeah, this is the one where it's like 50 turns, radius 2, spins in magnetic field. I have no idea like how they want me to like visualize it spinning. I don't really care. Honestly, we got formulas. That's all we need. So we say that, or it says that the flux varies sinusoidally because it's rotating against the magnetic field. So when you're like looking at it's equal to like integral B dA. Honestly, like the whole like integral stuff, I don't worry about it. What I would worry about is dA is so the area is constant. The area of the thing is just going to be like pi r squared, right? Because we're like, you know, assuming there's some stuff going on here, you know. So we care about this area here, which is that pi r squared. That's why they give us this r. Now, the magnetic field isn't super constant. They give you the B field, but you're not always going to be completely aligned with it. So what ends up happening is you have kind of like a field. It's not always the same. It oscillates sinusoidally. Now, when we get this EMF, we just take the derivative. What does that mean? Well, everything that's the same stays the same. This pi stays the same. This r squared is the same. Stays the same. This b stays the same. Since it's by t, we take the omega out through chain rule. We get cosine omega t. Since we want the like amplitude of the oscillation, yeah, that means we only care about this because we want the amplitude. So we can get rid of all this. And then we want to solve for this. So we have R, we have B. Do we have omega? Not quite. So we have the period of rotation, 1 second. So that means it takes 0.1 seconds per rotation. So if we want to go to omega, we invert that divided by 2 pi. So effectively, the idea there is it takes 0.1 seconds per rotation. So 0.1 seconds per rotation. If we invert that, we get 10 rotations a second, but omega always in radians a second. And a full rotation, think of like a circle, that's 2 pi radians. So it's 2 pi times 10 radians a second. So if you multiply that all together, you get pi r squared times t times 2 pi again times 10. You get an answer that is nothing like what is on the thing. What am I doing? Where's there? Is it 50? Oh yeah, and then you have to by the 50 because there's 50 turns. So joke's on you. There's another thing you have to multiply by 50 turns. So the EMF is 50 times as strong, or the flux I think even is 50 times as strong. Yeah, the flux even here should be multiplied by 50. So I end up getting 778,956. So it's the 8 because it's closest. It's very close to 8 in terms of value. Okay. So the wire in the figure, this one's increasing. So we see increasing, we know it's a flux problem. So we have a little loop. It's saying the area of the loop, treat it as constant, which essentially means like this is a point for all intents and purposes, and you can use this formula here. It's just so it can have a current induced. So let's solve here. Let's scroll down to flux here. So the way I like to look at flux, was I talking about this already? No, that was on the previous one. The way I like to look at flux, you want to assess a few things. So is the B field changing? So here, I'll give you a hint. Yes, the B field is changing. So I'll do over like dB. You ask yourself, oh, is the area changing? Here it is not changing, like the area here, which you're assessing over, it's not changing. Is the angle to the B field changing? No, it's not. So you don't have to put in an angle and then customary. Well, it's not customary, it's just right, but put in a DT there. So we have just the A here, which we can solve for. It's very. Then we want to take the rate of change of the B field. So what's actually happening? This is happening. The current in the wire is increasing. Well, how do we relate the current in a wire to the B field? Oh, wow, with this equation. So B is equal to mu naught I over 2 pi r, mu naught I over 2 pi r. This r is actually the distance, just so it doesn't get confusing, because there is a radius here. And I'll just write out here u naught over 2 pi d, because I is the actual thing, di dt, that matters. So what is given in the question? It goes from 1 amp to 3 amp in 1 millisecond. So this is just 2 amps per 1 millisecond. So area here for this, we're just going to sub in obviously pi r squared with this little r here. Plug everything in. So area here, pi 1 squared, u naught over 2 pi, like again I've said before, if you don't care about magnitudes, it's 2. Divide by, which is 5, sweet. And then 2 amps and 1 divided by 1. I got 2.5. So there you go. The answer with the 2.5. Funny one. So right after the switch is closed, what's the voltage across the resistor? R2. So right after the resistor closes, the thing about the inductors is they really try and like slow changes in like voltage and, well, I think it's current really. So the switch closes and instantly the circuit is flooded with current. But the inductor says, whoa, I'm used to having no current. I got to warm up first. So immediately they don't actually get the current. It's only after a while that they get the full current. So right now we treat it as a broken wire. We can effectively just say it's not there. We just have R1 and R2. R1 kilo ohm. R2 is like 2 kilo ohms. This is a red herring. And V equals 6 volts. Basically, you just divide proportionally. So this ends up being 4. This gets 2 volts. This gets 6. Woohoo. All right, it's a wibble wobble circuit with the capacitor and the inductor. So, the initial charge, which is good. Again, this is going to be like your big Q in the equations, because that initial charge, that's like how much energy really comes into the circuit, and then it'll get transferred like to the inductor. But when you get back to like all the energy being, it can only be so much as it was at the start in the capacitor. So we connect it to an inductor. What's the energy stored in the inductor? So when in doubt, work backwards, right? Energy stored in an inductor, it's Li squared over 2. So Li squared, I squared over 2. We have L. We need I. Well, okay, how do we get the I of a LC circuit? Oh, look, the formula sheet has something to say about it. I is equal to, negatives aren't real, omega q sine omega t. Phase angle aren't real. Ignore it. So now what? We have Q. Good. Like I said, it's charge. We need omega. Does the formula sheet have something? Yeah. I won't bore you with the flip back. It's this. Over square root LC. To get the omega, let's quickly plug that in. What do we got? 1 over 5e negative 3 times 2e negative 6. You get 10,000. So omega is equal to 1,000. Big number. So if we plug everything in, well, you know, we can plug anything in at this point. Make sure calculator set to radians. So sine of 10,000 times 0.23 times that 0.1 initial times that 10,000 again. We can square that value, multiply it by that, 5. I got like 206, so 2.1. Correct. Now we've added a resistor, and this will cause a damping effect as it wobbles between the capacitor and the inductor. We want to find the resistance R in ohms. What are we given? Well, we're given capacitor, we're given inductor, we're not given the resistance. We're given the initial charge, and we're given the charge later. Interesting. This seems like it will be a lot of work. Looking at what I did earlier, probably. So, okay, this is a undriven RLC circuit. We're lucky because, we only have, so we know what we have to use. We're assuming that W prime is just pretty much equal to W. I think on like another exam I did, practice exam, it was also like the same, even though it didn't assume it. Maybe check it on. Like, I think usually this is so minuscule compared to that it doesn't matter. Okay, so let's work through this. Q equals big Q E of negative RT over 2L, T over 2L. Now we do have this cosine term, but note that when we time equals 0 and the 10 complete cycles, those always represent like a complete cycle that's where the charge is maximized. So the cosine term represents in between those full cycles where, the the charge below its maximum, some of the energy will be transferred to the inductor. Since we're always just talking about max charges, we don't have to worry about the cosine term to diminish that initial Q. So, well, to find R, we have this Q, we have a certain T. Well, do we have a certain T? No, we don't. What we have is that 10 complete cycles later, the charge is this value. So how do we convert 10 cycles into a usable T value, time? What is happening? Why is that selected? That's annoying. That is weird. Well, that's a good question. 10 complete cycles. We have this. Omega. Love it. 1 over square root LC. If we calculate that, capacitor, inductor, capacitor, inductor, you get 1,000 here. Now, what is omega? It's the number of radians a second. That, like, I don't know. The rate of change in radians a second. Now, we have the number of complete cycles. Well, can we figure out how long a cycle takes? Well, certainly. If we have, how do we convert from cycles? So a full cycle is 2 pi radians. So if we take this 1,000 and we divide it by 2 pi, we can actually get the number of full cycles per second. And although here we want not the number of cycles per second, but the number of seconds it takes for a cycle. So if we do 2 pi over 1,000, that gives us the number of seconds. And then if we multiply that by 10, so 2 pi over 1,000 by 10, that will give us the time for 10 full cycles. Oops. So that all being said, we have the numbers to plug in, but we have to solve for R. So what do? Well, we start with this Q here. This question is just annoying, but it's okay. We're almost done. So we start here. We're at like 1 micro coulomb now. We divide by this big one, and we get 1/2, right? 1 divided by 2. So 1/2 to E times the whatever. So then we natural log both sides. We get natural log of 1/2 equals the whatever, right? And here it was the whatever in question, RT over 2L. So we can just shove this to the other side and we can get our R. So natural log of 1/2 by -1. We'll multiply by 2, we'll multiply by L. We'll divide by T, which again means dividing by 2 pi times 10 divided by 1,000. And then I did something wrong. Maybe. You gotta do most things right. Did I forget something? It was 5. It was 50. Divide by the time. The time it takes 10 times 2 pi divided by 1,000. What did I do wrong? It's not it, guys. It's not it today. 20 pi over 1,000. 20 pi over 1,000. Tripping. Let me just look at this. ln 2? Don't tell me. 6.28, yep. See? 2 pi divided by 1,000. 10 multiplied by 2, yeah. 10 times t, yep. Yep. I mean, this is the way to go. Is the ln2... I don't know. I think I'm just plugging into my calculator wrong. But this is the way to do it. Trust. Ln 1/2 e over 2l 1/2. Run it back. Multiply by 2. Multiply by l. Divide by t, which is 2, 3. And then times 10. I'm not getting what I want here. R. I'm solving for R. I don't know why this isn't working. This is the method that we here in the bottom. Wait, they do ln 2. Am I stupid? Am I incapable of dividing two numbers? Could be more likely than you think. Yeah. Hold on. Wait, what? Wait, what? Huh? 1 divided by 2 is 2? 1 divided by 2. I literally just put that as my calculator. I swear. I just put that as my calculator. Yeah. This is the way to solve the problem. It's the method. This is the method that the solution recommends. I don't know. I'm a little confused that they divide 1 by 2 and then get 2. You know? Maybe I'm sure I'm overlooking something. I don't think there's something wrong with that. I'm just tired, so leave a comment, guys. Leave a comment. Okay, phase angle. Set your calculator degrees. This is the formula here. When you hear calculate phase angle, this is what you're using. Tangent of the phase angle is equal to XL minus XC over R. Let's see, this has a resistor and a capacitor. It does not have an inductor, so we can just get rid of this. And again, we have this hertz, so 1,000 rotations a second. If we want radians, which is what the omega is in, we multiply by 2 pi, so 1,000 by 2 pi, but I'm getting ahead of myself by what I want. Radians, well, we're solving for negative xc over... What the heck is this? I wrote k? R. And xc is equal to WDC, so what we really are solving for is negative 1 omega dc. I was like, what the heck is D? No. WCR. I'm just making... It is like, I'm just getting delirious, I guess. It's only 10. Daylight savings, it's crazy. Anyway, so you put that all into an inverse tangent. Where omega, which is 1,000 divided by 1,000... For God's sake. 1,000 times 2 pi times the capacitance, 10 negative 6 times 10, and you get 57.85. It's and then value of the inductance that maximizes the amplitude of a current given an RLC circuit. If there's a question like this, like think resonance, but if you want kind of like a walkthrough of what's happening, you have a source with an amplitude, you have a resistor, you have a capacitor, you have some mystery inductor. It may be a mystery capacitor as well, as it was in the Spring 23 exam. If you want to maximize the amplitude of the current, okay, yeah. In one of them, it says like maximizing the amplitude of the power, which also requires maximizing the amplitude of the current, but recognize that you'd have to minimize the denominator, which this is fixed in this problem. But essentially, you can make this term equal to maximize the denominator by setting xc equal to xl. And xc is 1 over omega c, and xl is omega l. The inductance is going to be 1 over w squared c. And again, it's going to be Hertz 100 times 2 pi for your omega. So 1 over 100 times 2 pi, square that, then dividing by 100, you get 2.5, whatever, 25. There you go, there's all the questions. I'm sorry this didn't work when I could have just lied and said it worked. You don't see what's going on. Anyway, again, this is the right way to solve it. It's the right equation. Maybe I did some math wrong somewhere. I don't want to, bog down this video with me sitting here trying to throw stuff into my calculator. That's not the point. So yeah, good luck with the exam. Hopefully you understand everything. And if you don't, reach out to me on like GroupMe or just like put it on the video. That would probably work as well. All right. Good night, everyone.